So we've already seen angular momentum when we have like something like a plate or a ice skater, where we have this is our direction of omega. So you can check with your right hand rule that in fact if you take that spinning, then it gives you an omega that's up, which would tell you the direction of angular momentum, because we know that L is equal to I omega. So that would be the direction of the angular momentum. Sometimes we have situations, though, where we have a particle that's not rotating, and we can still, oddly enough, talk about its angular momentum. And here's and use conservation of angular momentum. So here's our motivation. So this is a top view. I hope you can imagine this situation. So we have a merry-go-round that's at rest. It can rotate about its center. And we have a kid who comes and runs and jumps on the merry-go-round. So the kid runs and jumps, and then the merry-go-round suddenly rotates. And so we can actually do this from conservation of angular momentum. We can describe what's happening by saying, even though the kid is running in a straight line, we can describe the kid as having an angular momentum. So instead of looking at I omega, because that doesn't really make much sense for the kid, we can talk about, in fact, the angular momentum of a particle. So usually we make this a lowercase l, but you can use a capital L if you want. And so we can say the lowercase l, if we just say for particle, we can still use I omega. We're going to look at the magnitude of L. So I for one particle would just be mr squared, and omega we can say would be v over r, sort of our same thing. So this becomes mrv if things are lined up like the kid, where the speed is coming in at 90 degrees. Obviously, if the kid is coming in like this and jumps, then the merry-go-round is not going to spin around. So this gives us our magnitude, but it depends on the angle between the V and the R. And I don't think you'll be surprised to know that if this is R and this is our V, what we want is MRV sine of the angle between these two vectors. Because in this first case we have R, and for the green we have V, so 90 degrees gives me a 1, versus if I compare the R with the blue vector, we've got that our angle here is 0 degrees, so it doesn't cause it to rotate. So this will show up, we write this, not surprisingly, I hope you're not surprised, to see this is a cross product, right? Because we know the cross product, the magnitude of the cross product has to do with the sine of the angle between them. And it's a cross product that we recognize if we pull this R out, then this is R and this is momentum. So it turns out we say L is equal to R cross linear momentum, because that way the magnitude of L is R times the linear momentum sine of the angle between those two, which is R times MV sine of the angle between them. And you can check that the cross product works, because if we look at this top view, so I'll redraw it with our R and our V like this. There's V and there's R. So here's R and here's V. I know I've just repeated what I've done. Then if we want R cross P, so V is in that direction, which also means our momentum is that direction. If we do our right-hand rule, so we take our fingers in such a way that we have our R along the first finger, our momentum P along the second, then in fact that gives us an angular momentum, an L, that's out of the page. So when I do R cross P with my right-hand rule, the direction is out of the screen. So check that you get that answer. And if we looked at what direction this would rotate, like this, right? That's the direction it would rotate. If we use our curling right-hand rule and we put that up to the screen and curl around with that, then we can say, hey, that's also going to give me an omega out of the screen, which gives me the same direction for my angular momentum, whether I use this expression or this expression. These two expressions are the same. Now, the way this is useful is if we go back to this problem of the kid running and jumping on the merry-go-round, what we can do is say, if we treat kid and merry-go-round as one system, so there's V, so our system is all of these together, then once the kid is on the merry-go-round, and it's now rotating, then there's still our system, right? We can say that the sum of the external torques, certainly the kid exerts a torque on the merry-go-round, but the external torques outside of our system are 0, and so we can in fact say that our L initial must be equal to L final, and I'm just going to do the magnitudes here. And so if I look at this for the kid, because the merry-go-round is at rest, for the kid it would be MRV, as we've already seen, because our angle is 90 degrees, so sine of 90 is 0, is equal to now I of the merry-go-round, plus I of the kid sitting on the merry-go-round times our omega final. And so we could find our final speed based on how fast the kid is going when they land on the merry-go-round. And the kid sitting on the merry-go-round is still a point, so it's the moment of inertia of the merry-go-round, probably 1/2 if it's a disk, capital M times r squared, where that's the mass of the merry-go-round. And the moment of inertia of the kid would just be mr squared. So this assumes a disk, and this is treating the kid as a point because all of the mass of the kid is a distance r, basically, from the center. And so from that, if we had numbers, we could then find the final angular rotation rate, the angular speed, in terms of radians per second. So if the kid is running at 4 or 5 meters a second, then what does that translate into? Well, it's going to obviously depend on the mass of the merry-go-round and how big it is.